All right. Good morning and welcome back to statistics. So today we're going to start our journey into 7.3, which is the central limit theorem. So let me go ahead and share our screen and we can do some work. All right. So this is probably one of the harder sections conceptually that you're going to have to deal with. All right. So this is now, in the previous two sections, we were given something. We were always given, could be considered normally distributed or is approximately normally distributed. And we're not going to have that anymore. Okay. Now, the important distinction, I should say, is in 7.1 and 7.2, we were looking at an individual. Okay, so 7.1, 7.2, even in chapter 6, we were kind of looking at individuals. So we were talking about calculating a probability for an individual. What is the probability for a randomly selected person or thing? Okay. In 7.3, we're going to be talking about groups. Okay. So this is where we really get some power of statistics, is that we're not looking at an individual item, we're looking at a group of items. Okay. So one of the things that we want to do is we're going to say, well, what's the sample mean of that group? Okay, so we might have a population, right, of we'll just say 1,000 things. Okay, that's really small. And then we might have a group of those things. We might say, well, we're going to select a sample of 40 things. Okay, and we're going to look at that X bar. Okay, the average of that specific group. So in person, like in an in-person class, I usually talk about, like, if we divide the class up into like front and back, or front, middle, and back, or left side, middle, and right side, that kind of thing. And I ask them, like, okay, what do you think the average travel time to school was for each of those groups? Okay. Now, depending on how big they are, and assuming that the students are pretty much randomly distributed throughout the class, so the person, you don't have one group of people that commute from like Santa Fe to come down to C&M for statistics or anything. Or you don't have a whole bunch of people from, say, Berlin to travel up. Okay. We're looking for, like, maybe people who live across the street are going to school. There's a university across the street, and maybe their commute time is, 30 minutes. Well, not 30, but like their commute time is 10 minutes. Okay. Versus the person who's got to drive across town and often deals with traffic, maybe their commute time is 40 minutes. So we're looking for, like, what is the average commute time in that group? Okay, so that's going to be my X bar. Okay, that's the sample. That's the sample mean. Well, if you're going to take, like, even for a business, right? If I pick a business that, like, maybe, again, in the before times before COVID, but if I just group them up by floor, okay, and again, I'm assuming that what floor they work on is different than, like, where they live. Okay, like, not everybody who lives close works on the first floor. Okay, and not everybody who works really far away works on the 5th floor or whatever, 9th floor. So we're assuming some kind of a fair distribution of people throughout the building. And if you pick any particular floor, right, you're going to have an X bar. You're going to have a sample for, like, the first floor, and a sample for the second floor, and a sample for the third floor. Okay, so you can go through and look at that. That's what we're interested in, is, like, what's the sample average for the first floor for all the people that worked on the first floor? What was their commute time? Okay, now what I'm hoping that you're kind of seeing is like, well, they should be all about the same. These averages should be all about the same, but they're not going to be the same. They're not going to be exactly the same, right? So again, if I just pick like different departments, right? If I go to a school and I ask like the chemistry department and the English department and the history department, and I ask each one of them like, what was the average you spent on lunch this week? They're all going to be, kind of alike, but they're not going to be the same. So what we're trying to say here is that X bar itself, okay, is a random variable. And it depends on what sample you've taken. Okay, depending on, whatever you want to do, however you want to take those samples, okay, that those are going to be more or less the same, but they are going to float, okay? They are going to be a little different from each other as we go through, okay? So what we're trying to do, what we want to do with the central limit theorem is we're going to say, well, X bar itself is a random variable, okay? And X bar, we'd like it, okay? So X bar, if a sample size, so if n is greater than or equal to 30, okay, X bar, if n is greater than 30, we'll have a normal distribution. Okay, it's really kind of a cool thing. Okay, that's one place I would actually recommend reading your book, because they will go through and talk about like getting more and more and more samples, okay, more and more things in that sample, and you can see, right, they start off with like a uniform distribution. This is not normal, okay, normal being this way, okay. And if you just start taking samples out of your continuous or your discrete distribution, your uniform distribution, that after a couple, you're going to get a triangular distribution. Right? There's like n is equal to 3. You get a sample size. You get a sample mean looks like this. So this is X bar. Okay, this is the original X's. X bar. You just go like n is equal to 3. So you just pick 3 things out of here. And we do this over and over and over again. Okay, so I might have like 100 different X bars in here. Okay, the way they're going to distribute is going to look like a triangle. If we start taking n is equal to say 5, they get a little bit more. Okay, and by the time we get down to a sample size of n is 30 or more, no matter what you started with, you were guaranteed, right, to get X bar having a normal distribution. Okay. Now there is one exception. If the original variable, so we're just talking about the X, we're not talking about X bars, we're talking about X's. So if the original variable has a normal distribution, okay, X bar, no matter what the sample size, okay, this is no matter what the sample size, no matter what. Okay, no matter what the sample size, X bar is normal, or it has a normal distribution. Okay, so if they don't tell you anything about your X's, okay, so if nothing is known about X, then we need sample sizes of 30 or more to say X bar is normal. Okay. If we know that X is normal, then we don't need a sample size. All the X bars are normal, no matter what the sample size. So if X is normal, so this is an underlying variable. So X is normal. Okay, then X bar automatically is normal. Okay, so it's kind of like an inheritance thing, right? If X has this property, then X bar will automatically have that property. Okay, so if nothing is known, then we need a larger sample size to guarantee. And some distributions will give you normal a little bit faster, but we're not worried about which those are or how to tell which one those are. Okay, that's not for this class. We just know if X isn't normal, then we have to go n is greater than 30 in order to say that X bar is normal. Okay, and we are really good at calculating normal distribution. Well, we are really good at typing those things in the calculator and having the calculator produce normal probabilities for us. So it's the kind of thing where it's like, fortunately, you guys don't have smoking tobacco as a major health concern. When I grew up, that was a major health concern for a lot of people. A lot of people join like smoking cessation programs. They're like, I want to quit. It's hard. It really is. So if you're doing this, my heart goes out to you. It's a hard habit to break. I can't point. Say I have 30 people. I have 50 people in my smoking cessation seminar here. I can't point to one person and say you are going to fail. Okay, just like I can't do that to a stat. Nobody fails for the stats class, but giving up smoking is a very difficult thing, and lots of people do it multiple times. Keep trying. Okay, you'll get it, but you really will. But but I can't point to one person and say, well, I know the probability is that you are going to fail. But what I could say is, as a group, right, that I expect so many people are not going to make it. Okay, because as a group, I could say, oh, they have a normal distribution. I know as a group what that behavior is going to look like. Okay, but any one particular individual, I got nothing. Okay, I can't point at one person and say that's your probability. Okay, but as a group, we could say something. Lifespan distributions. Okay, so lifespan distributions, and it's kind of neat. It's like it doesn't really matter if it's a living thing or not. So it could be electronics, but lifespan distributions all have approximately the same kind of distribution. Okay, we call it a bathtub curve. And what we're looking at here is we have in humans and in living things and most things that are produced these days, we kind of have there's a slight little bump here. It used to be a lot higher. Thankfully, it's not. And this is not drawn to scale. Okay. So what this is saying, this is one individual lifespan. Okay. I think this is what they call a beta distribution. Okay. But we have some infant mortality. Okay, we have some infant crib death, that kind of thing, which is tragic and sad. We want to push this down as much as possible. Okay, but once a new human is beyond like that sudden infant death stage, like once a kid is 5, it's unlikely that the child is going to there's still accidents, right? There's still tragic things that cut down people really, really short in their lives. Okay, but they're smaller. Okay, your average 30-year-old isn't just going to suddenly die. It does happen. Okay, but it's a low incidence. Okay, so we have our curve, and as people get to the end of their lives, right? It's a 30-year-old isn't going to just catch a disease or get into an accident and just suddenly die. Okay, I mean, like I said, it does happen, but it's not likely. But a 60-year-old isn't going to be so lucky. I mean, you could, heart attacks start to happen, strokes start to happen. A 70-year-old, right? That That's about the time when, like, oh, I smoked a lot, or but people start to get to the end of their lives. Okay, fortunately, we're pushing that further and further up. Fortunately, we're pushing this part further and further down. Okay, but by the time you know, when your 80-year-old grandfather dies, like it's sad. I wouldn't call it a tragedy. It's a tragedy when a 5-year-old dies, but for an 80-year-old to die, I'm sure I'll feel differently when I'm 80. Okay, this is not to offend anybody, but it's not a tragedy when an 80-year-old dies. You're starting to expect it. Okay, it's still sad. I mean, nobody wants to lose a grandparent. Nobody wants to, you know, if you're older, nobody wants to lose a parent. But you know, by the time they're 90, we all know people like they're just done. Okay, by the time, you know, we don't really live. There's a few people that live to 100, but when that person passes away, right? If you're 103 grandmother, you only live longer than men. Um, if you're 103 grandmother, like again, it's sad when that person dies, but you don't. It's not like a tragedy. You were bracing for this, okay? But that's an individual. You take my graduating class. It was like the population of Albuquerque in my graduation class. Okay, he was huge. But you know, we look at what the average lifespan is, right? You get your, you know, maybe 75. Okay, we could hope for more, but whatever. But if I took every homeroom in my graduating class and kind of plot them like this, okay, so the average, you know, the average lifespan is what's going on here. If I pick any particular 30 people and we plot the averages here, like they're on average, this is the curve we're going to see. All right. So the groups of them, they're not going. They may, you know, they may not make it to this. One of them might, but as a group, their average lifespan is going to be closer to what the overall average is. Okay. And again, some people didn't make it even to graduation. It's just, again, it's just tragic. But you know, overall, these 30 people, right? If I just start taking groups of 35 or more people, then their average lifespans are going to fall on this particular curve rather than the individual. This is how life insurance companies figure out like what their premiums ought to be, because they know what the average lifespan is at any particular age. And that's what they use to charge your premiums. You guys remember doing the problem from chapter 6. We have to figure out, you know, what the expected value was. Like, how do you think they come up with what the premium should be? Is they use these tables to generate, like, well, we have a probability that somebody who's 83 years old has a 90% chance to live to 84. That's what we're going to use to charge them for their premium bill. Okay. And again, they're looking at groups of people. They're not, you know, the more information you can pile into this, the better estimate they're going to get. See chapter 5 with conditional probability. But you know, we're going to know something about this group. All right. So I'm sorry that was a little long-winded. I'll try to keep it shorter for the problem section. But the normal distribution we're going to have. So normal distribution of X bar, and I'm going to say something that's really terrible here. It's going to have an average and a standard deviation, right? So what is the average of X bar? And that is the overall population average. We're going to denote it like this, so we know we're talking about an overall population average, but you don't really have to, because mu, right, is the same as mu sub X bar. Okay, we're just making it real clear we're talking about the average of the averages. Okay, so we could say something clever like the average of the averages is the average. Okay, so that's this one. This is the average of technically the sample averages, right? So the average of the averages, right? This is the average. Averages is the average. Okay, I guess the feeling I made this worse. All right, but the overall average, the average of the sample averages is the overall average. Okay. The standard deviation now. Okay, so the standard deviation of X bar, we don't call it standard deviation. We call it standard error. Okay, so standard error is just a new word. It has the same exact job as standard deviation. Okay, so the standard deviation of X bar is equal to the overall standard deviation divided by the square root of the sample average. Okay, so the standard deviation, the standard error of X bar, okay, is equal to the overall standard deviation divided by that sample average. Okay, so there's certain things they're going to have to tell you inside the problem, right? They're going to have to tell you like what the overall average is. They're going to have to tell you what the standard deviation is. They're going to have to tell you what the, they're going to have to tell you what the sample average is. If that sample average, if that sample size, sorry, sample size here, if that sample size is less than 30, they're going to have to tell you things like it's, assume the underlying variable has a normal distribution. Okay, if they'll tell you that, you can't do the problem because you need more information. Okay, so what we're talking about, just to sum up, right? We're talking about groups of people. We're talking about the group's average. Okay, not an individual average anymore. We're talking about the group average. And then we're going to, from that, we're going to calculate the group standard deviation. Okay, the sample average is standard deviation. Okay, and we're going to calculate we're going to calculate probabilities based off of that. Okay, so as we go through, I'll remind us of some points as we're going through, because I know that was a lot to digest. Okay. What do you have to memorize? Okay, you have to memorize that the averages, the averages of the average is the average. Okay, and we have to know that the standard deviation is equal to the standard deviation over the square root of n. Okay, and we have to, of course, remember normal distribution. Okay, the X bar has a normal distribution provided n is greater than 30. Okay, greater than or equal to 30. Unless, of course, it says it's normal, then it's all normal. Okay. I'm not sure why mathematicians call everything normal. Okay, maybe it might be we crave that in our own lives. Okay, but I don't know. All right. So let's just take a look at some of the problems. Okay, the first one's going to be pretty standard, and then we'll take a break after like maybe the first 3 of these, so we can go on to the next ones. But maybe the first 2. But just to kind of go through this. Okay, so if you're in my class, what you want to do is you want to see if you could do it on your own, and then you want to follow up and say, well, okay, I'll watch the video. Okay, or you can speed through or click past it if you got it right. All right. I probably don't have anything important to say. All right. We have a population mean of mu is 26. We have a standard deviation of 3. Okay. Find mu of x and sigma of x for samples of n is equal to 25. We are going to round our answers to 1 decimal place. Okay. I would not feel comfortable actually answering this question because I don't have an n is greater than 30. I think what they forgot to put in here was that we'd have a because everybody has a mean and a standard deviation. Okay. Well, one thing doesn't, but they neglected to say normal. So if you were in a quiz, like did you need to say normal here? That would be a fair question. I think they did mean to say normal here. Okay, so my average, right? The average of the averages is simply the average. Okay, but my standard error of X bar, right? That is sigma divided by the square root of 5. Sigma divided by the square root of n. Okay, because they're just trying to get us used to like these calculations right now. Okay, so this would be 3 divided by the square root of 25. So that's going to be 3 over 5. If we have to put it in a calculator, just to practice, okay, we're going to say 3 divided by, okay, square root of 25. Parentheses. And you might have to figure out like where we're going to do with the parentheses here. Put those in there. Okay. If you type in 3/5, you'll still get 0.6. So you're going to have, right? I mean, is 26, and our sigma was 0.6. Okay. That, see, like I said, I have a feeling they meant to write down normal here, but they didn't. Right, this one I'm happier with because you have a sample size of 115, certainly bigger than 30. Okay. Will be drawn from a population with a mean of 48 and a standard deviation of 12. Use a TI calculator to do this information. Okay, so let's write it out first. Okay, in order so we can get some ideas what's going on. We want the probability that X bar is going to be between 45 and 50. What's the probability? Okay, what's the next part? I have no idea. Calculator a little early. All right, so we have our X, the mean of X bar, right? That is going to be 48. Okay, our standard deviation, our standard error, okay, is the standard deviation of X bar. Okay, so that's going to be the sigma divided by the square root of n. Okay, is equal to what's sigma? Standard deviation is 12 divided by the square root of 115. Okay, let me show you something in the calculator real quick. Okay, oh, what do they want to know? 45 and 50. Okay, so they want the probability that X bar is between 45 and 50. Okay, so because the standard deviation is actually, we're dividing it by something, it's actually getting a bit smaller. So if you could look at the first example we did, like just kind of like remembering that standard deviation is measuring the spread. What's the spread of my blue curve? It's huge. I wouldn't want to calculate that standard deviation. That's going to be a mess. But the standard deviation here, right, this normal distribution, it's going to be a little bit easier. Okay, so it's a much smaller standard deviation. That's what's going to be happening for all of our problems, is that the standard deviation of the average is going to be smaller than the overall standard deviation. Okay, because the average is not going to be spread out as much. Okay, so all right, we're going to go to norm CDF. Okay, so second function, norm CDF. All right. And we want to know between 45 and 50. Right? Remember, it's norm CDF low average. So this was mean. And then standard deviation. All right. So here's what we're going to do. We know what the mean is. The mean was 48, wasn't it? Okay, but the standard deviation, that's the tough one. So what we're going to do is we're going to type in 12 divided by square root of 115. All right. So you don't have to mess with, put another parentheses in because we have to get the first one. You don't have to mess with dealing with these numbers unless you want to. Okay, the calculator actually will handle the fact that you've got a square root inside of your deal. So it'll automatically do that for us. Okay. So we could calculate that. Okay, let's go with the 0. I lost it. 95938. 5938. This 8 is going to right? We round it, it's going to be 0.9594. Okay, so almost 95%. If we did calculate that, right, that would be 12 divided by square root of 15, 115. All right, about 1.11. I think it's 1.12. Let's double check. 1.12. Yeah. So I'm going to call that approximately 1. All right, because I'm just going to use empirical rule to kind of get an idea for it. We want to know what's our average. Our average is 48. What is 2 standard deviations away from 48? And that would be 50. 2 standard deviations down, right? 48 minus 2, that would be 46. So we're going to have a little bit more, but how much probability is between 1 and 2 standard deviations? About 95%. So it's not quite that. I would have actually expected a little bit more, but I'm not going to fight with the calculator. I typed it incorrectly. We're good. So 95, 94. There we are. 0.9594. All right. See. And then what's the 90th percentile of X bar? Okay. So all right. So here we're going to go with norm inverse. Okay, what's our probability? Probability is 0.9. What's our average? Our average is 48. What's our standard deviation? Well, it was 12 divided by the square root of 115. Okay, and that's norm inverse. Okay, and that's going to tell us what the value of X bar is. Right, so norm inverse takes a probability and turns it into a value. Right, so we're going to go back here. We're going to say second function distribution. You guys are the unlucky ones now, because to do this as a to do this by hand with a table, I felt that was kind of a pain. So I didn't ask a lot of these problems. But lucky you, right? This is not that bad. So I could start asking these problems and not feel guilty about asking them anymore. All right. So X is about 49.43. Okay, we could say 49.43. Yeah, you guys get to deal with this now. Right. But it's really not that bad. I mean, it's the calculator. We were doing the same problem in 7.2. We're going to do the same problem in 7.3. It's just more of the same thing with a little twist on it this time. Okay, you got to remember this one. All right, I'll tell you what I'm going to do. I'm going to stop here, and then we'll do the rest of these in the next video. All right, so good luck with this. Get started on some homework, and we can meet again.